Hi class, in today's video we're going to be talking about section 9.1, Determining Probabilities. Now, imagine we have a spinner. So like a spinner you might use on a board game, right? And you might have them color-coded, so red, green, blue, and yellow. And of course I have all those colors here. I probably could have shaded them in. Red, green, blue, and if I can find my yellow, Right, and so one rather simplistic way that we could make a spinner is if we would take, usually we'd use a paper clip, but I just have a binder clip here, so we'll use it instead. Right, and you put your pen there, and then you can spin it, right? And it looks like it's pointing up towards green. So when we spin the spinner, it lands on one of these four. You might say, well, it could land on a line in between, but we'll say if it's on the line, we'll spin again until we get the number we're looking for. Now, bear with me just a moment. I'm having some auto-focusing issues. All right, now we have the autofocus off. So, like I said, if we land on one of the lines in between, we'll spin again until it falls into just one of those categories. So if we think of spinning a spinner in this way, we can say this is an experiment. So an experiment is an activity whose results are outcomes of the experiment. So our experiment in this case is spinning the spinner. And the outcomes are either red, green, blue, or yellow. And so we have a fancy name for this set of possible outcomes, R, G, B, and Y of this spinner. This S is called the sample space, is the set of possible outcomes of an experiment. And in addition to writing it kind of in this set way, we could also use a diagram. So we could say that the sample space is our red quadrant, our blue quadrant. I said blue, I meant green. Our blue quadrant and our yellow quadrant. And if we would put those together, we would have a really rough looking circle. But we can also write it, so we can write a sample space as this set. We could use a diagram or picture that shows all possible outcomes, or we could use a tree diagram. So a tree diagram says from a given spin, we could either get red, or green, or blue, or yellow. And so let's talk a little bit more about the outcome, what we would expect to happen. So if we were to spin a spinner, and so I'm going to use my graphing calculator for this, you can see there's a spinner, and if I lift it up, you might be able to see a little bit better. But up here is a 1, a 2, a 3, and a 4. So my spinner looks like this. We have a 1, and let me match those colors in blue. Red is 2. The 4 is purple, and that 3 looks like it's black. So this is our spinner. So this is the spinner on the calculator. We have two ideas: experimental probability and for experimental probability, that's the long run relative frequency that an event will occur over or given many repetitions. So I'll make a table. We have our outcome. We have our count. And then our relative frequency. So the nice thing about the spinner here is I can spin it once, and so we got a 4. And if I go ahead, I'm going to spin it again. We got another 4, 3, 4, 5, 6, and it's counting how many trials we've done. I know it's a little bit blurry, but we have a 6 up there in the corner. 7, 8, 9, 10 spins so far. And so let's go ahead and add now 10 more spins. That's 20, 30, 40. Because remember, this is long run relative frequency. We'll add 10 more. Now we've done 50 spins. You can see it looks like 1's happened the most, followed by 4, then 2, then 3. And we can go ahead and add 50. So that's with 100 spins. And go 50 more for 150, and then I'll go ahead and stop with 200 spins. So here, my outcome can either be 1, 2, 3, or 4. That was blue, red, black, or purple. So now that we've done all of our spins, if we hit the over arrow, it'll select it. So it says the first one happened 45 times, 55 times, the third one 51 times, and our last one 49 times. And so since we had 200 spins total, that means that our relative frequency is 45 over 200, 55 over 200, 51 over 200, and 49 over 200. And so we'll go ahead and put some lines in to keep those separated. And let's get a decimal value for those. So if I go ahead and lose my data, quit my probability simulator, 45 out of 200 is 0.225. 55 out of 200 is 0.275. 51 out of 200 is 0.255, and 49 out of 200 is 0.245. And so that's 22.5%, 27.5%, 25.5%, and 24.5%. That's our relative frequency. And these are experimental probabilities. In the long run simulation, in this case we did 200 runs, that seems pretty decent. the relative frequency that any event will occur is represented here. We have about 22% of the time we get 1, about 27.5, 2, 25 we get 3, and 24 we get 4. Now, you might be thinking to yourself, but I would expect each of those a quarter of the time because there were 4 pieces and they were all the same. Well, that's called the theoretical probability. And so this is, by definition, the number of ways an event can occur divided by the total number of outcomes. You might be thinking, that's a relatively strange way of saying that. Well, if we say P of R, so this is the probability of it landing on red of our original spinner, or number 2 up here. Well, red, it can only land on red, right? Purple isn't also red, and none of the others are red. So the probability is one way it can land on red out of 4 possible outcomes. The probability of green, if I go back to my original spinner, G, R, B, Y. Probability of green is 1/4. The probability of black or blue is 1/4. And the probability of yellow is 1/4. And notice 1/4 is exactly 25%, right? It's 0.25. And so these tend to be pretty close because we did a lot of trials. And this is something called the law of large numbers. Law of large numbers. And because math doesn't come from nowhere, this is actually Bernoulli's theorem. So Bernoulli is one of the leading pioneers in probability theory. And it says, as the number of trials of an experiment increases, the experimental probability approaches the theoretical probability of the event. So what does that mean? So remember, we said that if we had a spinner with 4 segments, the theoretical probability of it landing on a 1 is 1/4. And so probability of it landing on a 1 is 1/4. The probability of it landing on a 2 is 1/4. The probability of it landing on a 3 is 1/4. And the probability of it landing on a 4 is 1/4. And so I'll just go ahead and hit plus 50 a couple times till we get it up there. And right, you can already see that they start to get a little bit closer in terms of how many. Looks like purple has a little bit of a lead, but blue's catching up. Now red and black have taken the lead. Right, one's caught up as it keeps going. Right, the difference between them isn't as noticeable. And I'll probably stop before too long. Right, as we do more and more trials, the actual experimental probability gets closer and closer to the theoretical. And so you're like, well, purple's falling behind. But if we keep going long enough, I've already broken 1,000. I need to stop soon. That looks good to me. 281, 291, 296, 284. So we have a total spread of only what? 281 to 296. 15. And 15 out of 1,152 is a really small number. And so, right, you can see as we get through more and more trials, the experimental probability approaches the theoretical probability. It may never equal it exactly because one is experimental and one is theoretical, but it approaches the probability. Now what if I said on this spinner, which is 1, 2, 3, 4, what's the probability of spinning a 5? So what's the probability or the likelihood of me landing on a 5? Well, 0. There is no 5 on there. So if an event cannot happen, the probability of that, so if an event, we'll call it A, cannot happen, the probability of that event is 0. Here A is landing on a 5. The probability of A, the probability of spinning a 5, is 0. Otherwise, the probability of an event is between 0 and 1, because we say if an event will always happen, the probability of that event is 1. So here, if I say what's the odds or the probability that we get a 1, 2, 3, or 4? Well, no matter where we land, we're going to get one of those numbers. So if A is that, the probability of A, the probability of our spinner landing on any of those is 1. Again, excluding the cross marks, because those can throw a wrench into our plan. So a probability, we have two types: experimental probability, which is what we actually get when we conduct an experiment; a theoretical probability, which is what we expect it to be based on how many possible outcomes there are and how many ways we can get the desired outcome. And those probabilities, therefore, range between 0 and 1, with 0 never happening, 1 always happening, and otherwise it's somewhere in between. Bernoulli's theorem tells us that as we conduct more and more and more trials, the probability that we get, our experimental probability, will approach the theoretical probability. So let's look at another spinner. And this is to look at disjoint probabilities. So now my spinner is going to have the numbers 1 through 8. And I'm going to say let A be the event that we get a 6 or an 8. And let B be the event that we get a 1, a 2, a 3, or a 4. What is the, and I'll put theoretical here in parentheses, theoretical probability of getting a number between 1 and 4. In other words, what is the probability of B? Well, since each spin can be a 1, a 2, a 3, or a 4, or a 5, or a 6, or a 7, or an 8, but can only be one of them. These are disjoint outcomes. The probability of B is really just the probability of a 1 plus the probability of a 2 plus the probability of a 3 plus the probability of a 4. And remember we said theoretical probability was the number of ways we can get that outcome. Well, we can only get a 1 one way if it lands on the 1, and there are 8 possibilities. If it lands on a 2, that can only happen one way, 8 possibilities. It can only land on a 3 one way, 8 possibilities. It can only land on a 4 one way, still 8 possibilities. So that tells us that it's 4 out of 8, or 1/2. And now this kind of matches our intuition, right? Because if we go into our spinner, and now I'm going to increase it to 8 of them. I'm going to clear my data. 1, 2, 3, and 4 is this top half of my spinner. So I would expect that half of the time it's going to land on the top half, and half of the time it'll land on the bottom half. And to give you a definition, the probability of an event, and we'll call it B, because that's what we called it, is equal to the sum of the probabilities of disjoint events whose union is the event. So if I would take the union of that set containing 1, 2, 3, 4, that is precisely B. So our friend set theories coming back from very early in the course, resurfacing here, because B of getting 1, 2, 3, or 4 is the union of each of these, so we find the probability of each, we add them up, and we get 1/2. Now, if we have two events, so we have our events, A was 6 and 8, and B is 1, 2, 3, and 4, we say two events are mutually exclusive if their intersection is the empty set. So since the spinner in one spin can't land on 6 or 8 and 1, 2, 3, or 4 at the same time, A and B are mutually exclusive. And so notice the probability of 1 and the probability of 2 are mutually exclusive. The probability of 2 and 4 are mutually exclusive because they can't happen at the same time. And an important result is if A and B are mutually exclusive, the probability of A or B, A union B, is the probability of A plus the probability of B. So the reason we have this disjoint events lets us add this up is because they're mutually exclusive. And so here, I could say the probability of A or B, so the probability of 6 or 8 or 1, 2, 3, or 4 is just their sum. So A can happen 2 out of 8, and B can happen 4 out of 8, which is 6 out of 8, or 3/4. So again, if we look at our handy calculator and look at our spinner, 1, 2, 3, or 4, that's half. 6 and 8 are 2 more 8s, so only 2 of those 8s aren't covered. And so we would expect that 3/4 of the time, so 3/4 of the time, we'd land on 1, 2, 3, 4, 6, or 8. But again, we can only do that when they're mutually exclusive. So I'm going to introduce one more idea and then talk about what happens if they're not mutually exclusive. So we have the notion of complementary events. If A is an event, and A in this case was 6 or 8, then A complement is its complement. Remember, we had the complement of a set, and that's the set here, which is going to be our sample space, minus our set. And so our sample space is 1, 2, 3, 4, 5, 6, 7, 8. Take away the 6 and the 8. And what are we left with? Well, we're left with 1, 2, 3, 4, 5, and 7. And that is a complement. So a complement is 1, 2, 3, 4, 5, 7. An important follow-up is the probability of a complement is 1 minus the probability of A. And let's kind of work on proving that to ourselves. Well, the probability of A is 2 possible outcomes out of 8 total, which is, if we take 2 8s to convert it to a fraction, 2 8s gives us 1/4, or 0.25. That was much harder to think through than it should have been. So the probability of a complement, if this equation is right, should be 1 minus 0.25. Well, that's 0.75. Well, what do we know the probability of a complement to be? So that's the probability of 1, 2, 3, 4, 5, and 7, which is 1/8 plus 1/8 plus 1/8 plus 1/8 plus 1/8 plus 1/8, which is 1, 2, 3, 4, 5, 6 eighths, which is 3/4 and 0.75. We can also think of it this way. We know that the probability of A or its complement is 1, right? Because either it's going to fall within one of 6 or 8, or it's not. And we know that A intersect A complement is the empty set from our set theory days, or from looking, they have nothing in common because we did the minus operation. Well, that means that 1 equals the probability of A plus the probability of A's complement. And to get it to look like this, subtract the probability of A to both sides, and we get the probability of A complement is 1 minus the probability of A. And so this here motivates it, and this is more of our proof. So when we have complementary events, we can find the probability of one by taking one minus the other, right? Because this also then shows us that the probability of A is 1 minus the probability of A complement. So if you're given one, we can very immediately get the other. And now I said, what happens if they're not mutually exclusive? Non-mutually exclusive. Well, let's write our sets. So we're still working with our spinner with 8. So A is the set containing 6 and 8. B was what? 1, 2, 3, and 4. And A complement we said was 1, 2, 3, 4, 5, and 7. Are B and A complement disjoint? No. In fact, they're not mutually exclusive because their intersection is not the empty set. So are they mutually exclusive? No, because A complement intersect B is 1, 2, 3, 4. Those are common to both. The probability, so the probability of non-mutually exclusive events is, got ahead of myself, given by the probability of A's complement or B is the probability of A complement plus the probability of B minus the probability of the intersection of A and B. Now let me break this down. We can find the probability of A complement directly. It's 1, 2, 3, 4, 5, 6 out of 8, right? We know that's 6 out of 8 because of our spinner. Well, the probability of A complement is 1, 2, 3, 4, 5, 6. Oh, that's what I just said. Of, I got ahead of myself, A union B. 1, 2, 3, 4, 5, 6. Nope. 5, 7. There we go. Probability of A complement union B. This set, 1, 2, 3, 5, 7, 8. 1, 2, 3, 4, 5, 7, 8 is 6 out of 8. Well, that's the probability of A complement, 1, 2, 3, 4, 5, 7, which is 6 out of 8, plus the probability of B is 4 out of 8, minus, well, what's A complement intersect B? So that's what's common to both of these. The probability of 1, 2, 3, 4. Minus 4 out of 8. And so 6 eighths plus 4 eighths minus 4 eighths is, in fact, 6 eighths. But let's think through this. Why is it that this non-mutually exclusive probability, we have to subtract something off? Well, let's think about it this way. If I want A complement union B, the probability of A complement says, well, that's the odds of me getting a 1, a 2, a 3, a 4, a 5, or a 7. Or the odds of getting a 1, a 2, a 3, or a 4. But I've doubly counted, right? These were all double counted. And so if I do A complement intersect B, that's exactly those 4 that I will have double counted. So we take the probability of A, complement in this case, probability of B, minus anything that was double counted. So bringing that together, and I'll put my little summary sheet here. An experiment is an activity that has an outcome. The sample space is the set of possible outcomes. If we had a spinner, it could be green, red, blue, and yellow, and we could represent with that our sample space set, a drawing, or a tree diagram. Experimental probability is real-world results of what we get by repeating that experiment a large number of times. But the theoretical probability, and the one we use more often, is the number of ways an event can occur divided by the total number of outcomes. Thinking about our spinner, we expect it to be 1/4 of the time each of those, and that's where that comes from. Bernoulli's theorem says that as the number of trials increases, this experimental probability approaches the theoretical probability. And probabilities can be as small as 0 when something can't happen, as large as 1 when it'll always happen, and otherwise it's somewhere in between. If probabilities are disjoint, we can just add the probability of the individual events to get their probability of the larger event. So the probability of getting a 1, 2, 3, or 4 was the probability of 1 plus the probability of 2 plus 3 plus 4. If they're mutually exclusive, the intersection of two events will be the empty set. And whenever that's the case, we can find their probabilities by adding them together. We define complementary events as an event that is the complement of some other. So it's the what happens if that doesn't happen. And whenever we have two events that aren't mutually exclusive, the probability isn't just the probability of the first plus the probability of the second. We also have to subtract off the doubly counted pieces from both. And so we're going to spend the next couple of videos working with probabilities, but this is your kind of orientation to probability. Have a great day, everybody.